So welcome to the solution of part B. Let us just try to read through this exercise first. What we are asked to do is to calculate the expected present value that is given here of a life insurance contract that looks like so. So the product that we're actually looking at is a so-called deferred temporary life annuity due. And as we just explained in the earlier video, what happens is we wait K years and then start payment with 1 unit each year, lasting until time K plus N minus 1, where the last payment falls, so long as the person is alive, right? So if the person dies here, then the last payment falls here, and then there won't be any more payments. What we're asked to do now is to calculate the so-called expected present value in terms of TPX, and then show that the expected present value is equal to the expected present value of certain other products. So first of all, some of you might ask, well, what symbol can I use to denote this thing? Now, you might note that what is inside is the present value of the payment stream, where we take each payment in the payment stream and discount it back until time 0. The reason we take the expected value outside is because each of these payments will only fall depending on whether or not you're alive, which means that B of t does not have a concrete value, for example, for t equals to k. It might be 0 if you're alive at time k. It might be 1. Oh, no, it might be 0 if you're dead at time k. And if you're alive at time k, it will be 1. So what does this mean? This means that in order to get a number that we can use to price the contract, we need to take the expected value of the present value. So this is the expected value of the present value. And what we actually have here is the thing that we call V of 0 minus, where we stand right before time 0 and consider the expected present value of all of the future benefits. The reason why we don't write V of 0 is because V of 0 is actually the expected present value of all of the benefits discounted back to the present, where we only look at strictly future benefits. So in that case, we would sum from time 1. But what we want here is to sum from time 0. And in order to include time 0 as a future benefit, what we will have to do is, to use this notation V of 0 with a little minus just right in front. So with that being said, let us just take a quick look at the different things in this part of the exercise. So what we start with in each exercise is always to write up the definitions of the things we're looking at. So we want to write up the expected present value in terms of TPX. So what was TPX? TPX is the conditional survival function. And it is given as the probability that given a newborn survives past age x, then that newborn will survive past age t plus x. We can also write it as the probability that the remaining lifetime of an x-year-old exceeds t years. So that was TPX. What we want to show is that the expected value of this present value is equal to this thing. Now, first of all, what is this thing even? That is the second thing that we need to make clear. So what is KEX? KEX is the expected present value of a pure endowment insurance of K years. And what is a pure endowment insurance of K years? It means that we're looking at a contract where if you're alive at time K, given that you are X years today, then you will have a payout of 1 unit at that time. that also means that the expected present value of this is the probability that you will be alive at time k, given you're x years old now, and then multiplied by the value 1 that you will be paid out. So that's just a 1 that's invisible. And then you take that value and you discount it the k years back to now. And the other symbol, a umlaut x plus k something weird n, what does that stand for? Well, that stands for the expected present value of a temporary life annuity due. So with expiry in years, and then assuming that you are x plus k of age today. So that's what the x plus k stands for. If the x plus k had been here instead of here, then what we were looking at would just be a normal annuity due, which has been deferred, and not a temporary life annuity due. So when the x plus k is here, after the a, it means that we're assuming we're looking at an x plus k year old right now at time 0. And we draw the contract with an expiry of n years. So what is this kind of temporary life annuity due? It means that assuming you're alive, then you will receive payment once in the beginning of each year, beginning at time 0 all the way up until time n minus 1, given you're alive. So this present value, expected present value, is given as the sum from for t equals 0 up to k to n minus 1 of pure endowments that each last t years for an x plus k year old. It kind of makes sense if you think about what a pure endowment is and what a temporary life annuity due is. Then a temporary life annuity due is essentially just a sum of pure endowments. So this thing here, if I should write in the definition of the expected present value of the pure endowment, would then be the sum from 0 up to n minus 1 of tpx plus k multiplied by e to the minus delta t. So now I have these two expressions here, and I also know what each of these symbols mean. So just before we start the calculations in the next video, let's think about why we even want to show this. Like, why do we want to show this weird thing? And the reason we want to show this weird thing is because we want to show that the expected present value of a contract where we wait k years, then receive one payment if we're alive at time k, and then receive payments for the beginning of each year for n years if we're alive at each of those years. Well, we kind of want to show that such an expected present value of such a contract corresponds to the expected present value of a contract where we are looking at you surviving past the first k years, then receiving a payment at k, and then receiving a payment for each year that you survive as an x plus k year old. So it kind of sort of makes sense in a weirdly intuitive kind of way. So now we just want to see if we can make this whole thing make sense in the mathematical sense as well.